Something out there just changed, fast, quiet, and far bigger than expected. A dark visitor from another star has crossed into our solar system, and the newest readings say we may have badly underestimated what it is. Not by a little, by enough to change the whole story. If you think this is just another comet, wait. Because what scientists found buried inside this object could tell us where it formed, how long it drifted alone, and why the final part of this encounter may matter more than anyone first realized. The object is called 3I/Atlas, and even that name tells you this is rare. The 3 means it is only the third confirmed interstellar object ever seen passing through our solar system. The letter I means interstellar, a traveler from the space between stars. And Atlas is the survey system in Chile that first caught it, almost by accident, as a faint moving blur against the dark. That first sighting happened in early July of 2025. The NASA-funded Atlas survey, the Asteroid Terrestrial Impact Last Alert System, was built for something much more ordinary. It watches the sky for rocks that might threaten our own planet. So the moment it picked up a smear of light moving wrong against the background, the alert went out. Within hours, follow-up telescopes confirmed what no one dared say at first. This was not from here. At the time, it looked like a strange little point of light moving too fast and at too sharp an angle to belong here. It was not looping around the sun like a normal comet born in our neighborhood. It was cutting through on a path that said something much more dramatic. This object did not come from the outer edge of our own solar system. It came from somewhere else entirely. That matters more than it sounds. Every comet in our solar system carries clues about our own past. They are leftovers from the early days, old frozen pieces from when the planets were still forming. But an interstellar comet is different. It is a sample from another star system, a real piece of another cosmic history, not an image, not a theory, not a computer model, the thing itself. Ice, dust, chemistry, motion, all of it crossing our path for a brief moment before vanishing back into the dark. And this one did not arrive quietly for long. Within days, astronomers saw that it already had a coma, the glowing cloud of gas and dust that forms when a comet warms up and starts releasing material into space. That was odd because it was still far from the sun, out near Jupiter's distance. At that range, many comets are still sleepy and dim, but this object was already active. Something inside it was volatile enough to start escaping early. Right away, that raised a deeper question. What kind of ice starts venting from that far out? Water usually needs more heat. So if this was not mostly water leading the then what was it? That question pulled in some of the most powerful tools we have. Hubble watched it, Webb watched it, other space missions and ground telescopes turned to follow it. Scientists knew they had only one chance. Interstellar objects do not circle back for a second visit. They arrive once, they race through, and then they are gone for good. And here is where the story starts to bend. At first, nobody knew how large the solid core really was. All anyone could clearly see was the bright haze around it. Imagine trying to judge the size of a coal ember hidden inside a bonfire's smoke. That was the problem. The coma was glowing. The dust was reflecting sunlight. The actual nucleus, the hard, icy body in the middle, was buried under its own activity. Early estimates were all over the place. Maybe it was only a few hundred meters wide, maybe much larger. The official range was broad enough to leave huge room for doubt. And that uncertainty shaped the way the public heard the story. Some people pictured a modest comet from another star. Interesting, yes, but not extraordinary. Others suspected the real answer could be much bigger. Then came the chemistry. When the James Webb Space Telescope examined the object, it found a gas mix that did not look like a typical solar system comet. The coma was unusually rich in carbon dioxide, while water appeared much weaker than expected. That alone made scientists stop. Most comets we know release plenty of water once they begin to warm. But this visitor seemed to be playing by a different rulebook. The numbers were striking. Reported in a paper led by Martin Cordner and his team, the carbon dioxide to water ratio in the coma was measured at roughly 7.6 to 1. Put another way, for every molecule of water venting away, more than 7 molecules of carbon dioxide were coming off. That figure sits far above the trend seen in known solar system comets by several standard deviations. In other words, not a small difference, a genuine anomaly that suggested a different birth environment, a different freeze, a different history. And if the chemistry was different, maybe the object itself was different too. Think about what that means. You're not just looking at a snowball in space. You're looking at preserved material from another system that formed around another star, under conditions we are still trying to imagine. This is the kind of thing astronomers dream about, because it is the closest we get to bringing another solar system into the lab without ever leaving home. But the biggest surprise was still ahead. To separate the solid nucleus from the surrounding cloud, researchers had to model the coma very carefully and strip away the extra glow. That is delicate work. A small mistake can change the answer by a lot. Too much subtraction, and the nucleus looks smaller than it is. Too little, and the dust makes it look larger. So teams kept comparing data, testing assumptions, checking how dark the surface might be, and asking the same question again and again. The arithmetic behind that separation is not simple. Researchers assume an albedo for the dust and guess how compact the coma is. They must decide whether the body vents more gas on one side, like a single nozzle, or spills evenly like steam from a kettle. Each choice nudges the final estimate up or down. What is really hiding in the middle of this thing? The answer that emerged was much more dramatic than the small early guesses. The nucleus appeared to be on the order of a few kilometers across, with one estimate placing it at about 2.6 kilometers wide. That does not sound giant until you remember how mass works. Double the diameter, and the mass does not just double, it rises fast, cube fast. So a change in size like that is not a minor correction. It turns a small visitor into a far heavier one. Suddenly, 3I/Atlas was no longer just the third confirmed interstellar object. It looked like the biggest confirmed one ever observed by a wide margin. It is worth pausing on what those numbers actually mean in plain language. A nucleus around 2.5 kilometers in diameter is not a pebble. It's a small mountain of ice and dust drifting between the stars. And the published range, from roughly 300 meters at the low end to about 5.6 kilometers at the high end, already spanned an order of magnitude before the latest modeling tightened it. That is a wide bar of uncertainty for science that wants to be precise. It is also why each new measurement, each new paper, each new instrument reading can move the story more than people realize. And that is when the whole mood changed. Because size is not just a number. Size changes what the object could preserve. It changes how long it can hold heat. It changes how deep old layers might survive below the surface. It changes how much of another star system's history might still be locked inside. Let me ask you this. If you were the scientist staring at that data for the first time, would you trust the old picture? Or would you start wondering what else you had missed? That is exactly what happened next. Researchers began looking harder at the age question, not the age of the object as a neat single number. Because that part is still debated, but the age of the material itself and the kind of environment it must have come from. The fingerprints were buried in the isotopes, especially in the water. Some studies suggested the ice carried an unusually heavy form of hydrogen called deuterium at levels that point to extreme cold during formation. That matters because isotopes are like accents in a voice. They tell you where something may have grown up. They are not always easy to read, and scientists argue over the details, but they can reveal whether an object formed in a warmer inner region, a colder outer region, or somewhere stranger than either. In this case, the signal pointed toward severe cold, deep cold, the kind of cold where chemistry slows, where fragile compounds can stay locked in place, where a body can hold onto a history that would be erased in a hotter place. Some researchers even argued that the object, or at least some of its material, may predate our solar system by a large margin. Pause on that for a second. You're living on a planet that formed around our sun. Everything human has happened here, in the tiniest blink of cosmic time. And now, for a few short months, our telescopes may be watching ice that formed before Earth existed. Maybe long before. Ice that spent ages in darkness no human mind can really picture, crossing empty space between stars, untouched except by radiation until it finally wandered into our sky. The published work, again from the Cordner Group, suggests the water in 3I/Atlas is enriched in deuterium above the values typical for our solar system, and that this composition fits a body that may have accreted somewhere between 10 and 12 billion years ago. If that holds, then the parent star system in which this comet first froze may no longer even exist. Stars live, swell, die. A long-lived low-mass star can outlast its smaller neighbors, but a whole planetary nursery around an early sun would not. The home that built this ice is, by now, almost certainly gone. The word cold here does not mean winter. It means temperatures low enough that simple molecules had only the slowest paths to react and stick. In that slow chemistry, heavier isotopes like deuterium get preferentially trapped. A deuterium-rich. Reading locked into water ice behaves like a delayed thermometer from a nursery that no longer exists. But here is where things take a strange turn. If this comet had been carrying methane near its surface all along, astronomers expected they would detect it earlier. Methane is volatile. It turns to gas easily. A body warming up on the way toward the sun should have shown that signature sooner if the methane had been sitting close to the top. But early observations did not show a clear methane signal. Then, after the object swung around the sun and started heading, back out. Webb looked again. This time, methane was there. For the first time on an interstellar visitor, methane gas was directly detected around it. Not a vague, maybe. A real spectral signature, clear enough to set off a fresh wave of excitement. That immediately raised another question. Why now? The leading idea is both simple and eerie. During its long journey through interstellar space, the surface of the comet may have been altered by cosmic rays, not light, not heat from a nearby star, but high-energy radiation crossing the galaxy, slowly changing the upper layers over immense spans of time. Over long enough periods, that can build an old, weathered crust, a processed outer shell that no longer behaves like the cleaner material underneath. So when 3I/Atlas first approached the Sun, what we were seeing may have been only the surface story. The Sun heated the outer shell. Gas escaped, yes, but not everything trapped deeper down. Then came the close pass. More heat, more time, more pressure. And at some point, the warming may have reached lower, fresher layers where methane ice had remained protected. Once that happened, the object started releasing a deeper memory of itself. That idea is astonishing. It means the first observations may not have shown the comet's true inner chemistry at all. They may have shown only the scarred skin it grew while wandering the galaxy. The later observations may have been this moment that skin cracked enough for us to glimpse what had been hidden underneath for perhaps millions, maybe billions of years. And suddenly the central mystery was no longer just how big it is. It became this. What exactly has our sun opened? Scientists love moments like this because they turn a simple object into a layered story. First discovery, then classification, then size surprise, then strange chemistry, then a delayed methane release that suggests buried material from deeper inside. Each answer opens a new door. Each new door reveals a darker room. This is also where public imagination tends to sprint ahead of the data. Whenever something unusual appears in space, especially something from beyond our system, people start asking if it could be artificial. That happened with Oumuamua. It happened again here. A few high-profile voices floated bold possibilities once the chemistry and behavior of 3I/Atlas started drawing attention. That made headlines fast because mystery plus space plus what if is always powerful. But the scientific response was more careful. Teams looking closely at the data said the object still behaved like a natural comet. A very old one, a very strange one, a very important one, but still natural. The gas release, the dust, the coma, the trajectory, the chemistry after heating, all of it could be explained by known physics once you account for how long this thing may have traveled and how altered its surface may have become. That did not stop researchers from checking. In fact, one of the most serious follow-ups came from techno-signature searches. Breakthrough Listen and collaborators used radio telescopes to scan the object for any sign of artificial transmission. They went through millions upon millions of narrowband signals. At first, some candidates stood out, which is normal in a noisy sky packed with human technology. But after filtering and checking, the signals traced back to ordinary interference, not a beacon from the comet. That is science at its best, not a dramatic yes or no shouted on day one. A test, a search, a filter, a result, no evidence. Of alien technology, no sign of an onboard transmitter. Just a natural interstellar comet that turned out to be far more interesting than the simplest version of the story. And honestly, that may be the most awe-inspiring outcome of all, because nature does not need help being incredible. Think about the sequence here. A survey telescope built to watch for dangerous near-Earth objects spots a faint smear of light. Astronomers realize it is interstellar. Major observatories lock on. Early estimates keep the solid body uncertain. Then deeper analysis suggests the nucleus is much larger than the modest first picture many people held in mind. The chemistry looks odd, rich in carbon dioxide and weak in water compared with many local comets. Later, methane appears after the solar pass, hinting at a buried inner layer newly exposed to heat. And every step of the way, the object keeps racing onward, indifferent to our surprise. If you enjoy space stories like this, the ones where a single object rewrites the script in real time, this is exactly why Galaxy Sphere exists, because the universe rarely tells us the whole truth at once. Now let's talk about what scientists in the field actually do with a case like this. First, they compare it to the only other interstellar visitors we have. Oumuamua was the first, discovered in 2017, and it was deeply strange in its own way. It did not show the kind of obvious comet activity people expected, which is one reason it sparked so much debate. Then came Borisov in 2019, which looked more clearly comet-like. That gave astronomers a second data point, but only barely. Two examples are not a population, they are a tease, and the difference between those first two matters more than any list. Oumuamua arrived looking dry, with no clear plume, no obvious gas. Borisov showed up dressed like a normal comet, with a dust tail, confirming comets can really survive a journey between stars. Both were tiny, both were faint, both left us wanting more. 3I/Atlas. Is the first one generous enough to give us more? It appears brighter, more active, and likely more massive than Borisov. It gives us stronger chemistry, stronger dust signals, more opportunities to compare how another planetary system builds icy bodies. And comparisons matter. If interstellar visitors all looked basically alike, that would tell one story. But if they vary a lot in chemistry, size, and behavior, that tells another. It suggests other star systems may build and eject small bodies in many different ways. Different temperatures, different disk chemistry, different mixing of rock and ice, different bombardment histories, different architecture around their parent stars. In plain language, this comet may be proof that our solar system is not the standard model of everything. It may be only one local version of a much wider cosmic menu. That is the emotional peak of the story, and also the hardest thing to fully feel. Because the science is made of spectra, models, and quiet arguments over data. But behind all that is a very human moment. People on one small world realized they were looking at matter from another one. Matter older than memory. Matter that crossed the gulf between stars and arrived just in time for us to notice. What would that feel like in the control room? Not fear, not even triumph. At least, not at first. Probably disbelief. Then caution. Then that strange mix of calm and adrenaline that comes when you know the clock is running and the universe has handed you something rare. You would know that every hour matters. Every observation matters. Every missed window is gone forever. And while scientists were doing that work, the object kept moving toward the part of its path that made later observations even more urgent. It passed near Mars's orbital region. It moved behind the sun from Earth's point of view for a time. Then it came back into view and continued out toward Jupiter and beyond. That outward leg is important because sometimes the way a comet behaves after heating tells you more than the way it behaved before. The inside starts speaking. Volatile compounds turn on or shut off. Dust changes. Gas ratios shift. In a sense, the object stops introducing itself and starts confessing. That is why the methane result mattered so much. It was not just another chemical line on a chart. It was a sign that the comet's story had changed between the inbound and outbound phases. The object we thought we knew before perihelion was not the same object we were reading after. And that brings us to the expert reaction, which was not one single message, but a layered one. The first reaction was excitement, because interstellar objects are rare enough that every clean measurement feels precious. The second was caution, because large claims need strong checks. The third was debate, especially over age, origin, and just how unusual the chemistry really is compared with the edges of what we already know in our own solar system. Some scientists leaned into the idea that the object formed in an unusually cold outer environment around another star. Others focused more on long exposure to radiation as the key to understanding the altered surface and the delayed methane. Some emphasized that we should be careful about saying too much from only one pass and a narrow observing window. That caution is healthy. Space science is full of moments where the first dramatic interpretation softens later. But it is also full of moments where later data makes the original story seem too small. With 3I/Atlas, that second pattern may be closer to the truth. The more we looked, the less ordinary it seemed. Not supernatural, not impossible, just deeper than expected. That distinction matters because public interest often swings between two extremes. Either an object is sold as a world-ending threat, or it is treated as overhyped nothing. This comet was neither. It posed no danger to Earth. It never came remotely close enough for that. Its importance was never about collision. It was about access. Temporary, accidental access to material from another star system. There is a lesson in that. Sometimes the biggest space story is not an explosion, a planet-killing rock, or a glowing alien city in a telescope frame. Sometimes it is a faint, dusty object with a difficult orbit and chemistry that refuses to fit the easy box. Sometimes the most profound thing in the sky is a clue. And 3I/Atlas is full of clues. Its speed tells us it was not bound to our sun. Its orbit tells us it came from outside. Its activity far from the sun hints at volatile material that behaves differently from many familiar comets. Its carbon dioxide-rich coma suggests a formation history, unlike the usual patterns we see close to home. Its later methane signal hints at buried inner layers protected by an ancient outer shell. Its estimated size says we may be dealing with a much more substantial body than the early modest picture suggested. Each clue narrows the possibilities. None of them solves everything. That unresolved middle is where the real wonder lives, because we still do not know the parent star system it came from. We may never know. The Milky Way is not a tidy map where every drifting object carries a return address. By the time something like this reaches us, it has spent so long in motion that tracing it back through the galaxy becomes almost hopeless. Gravitational nudges, stellar encounters, the slow churn of the galaxy itself, all of that scrambles the trail. So we are left with a messenger whose language we can partly decode, but whose home we cannot name. That is haunting. It means 3I/Atlas is both intimate and unreachable. We can measure its gases. We can model its dust. We can estimate its size. We can watch sunlight. trigger buried methane. But the world that made it may remain forever beyond our grasp. And still, even that is enough to change how we see our place in space. For most of human history, other solar systems were pure imagination. Then we found exoplanets and learned that planets are everywhere. Now we are entering a stranger phase where parts of those systems may come to us. Not often, not in a controlled way, but enough that we can begin building a real comparative science of alien leftovers. That is a wild sentence when you think about it. Alien leftovers. Not life, not ships, just old frozen debris from another star. Yet even that is revolutionary. Because debris remembers. Debris preserves temperatures, ratios, layers, and chemical choices made during formation. Debris can tell us what kind of nursery built it, what kind of cold shaped it, and how violence or radiation changed it over time. In other words, debris can answer questions that planets alone cannot. And this leads to the bigger picture. Why does a single comet matter to people who will never read a spectroscopy paper? Why should anyone care whether methane appeared after perihelion instead of before? Why should the size correction matter outside the astronomy community? Because the core question underneath all of it is the same one that has followed us for generations. How unusual are we? Not just Earth, not just life. Our entire system, our recipe, our history, every interstellar object gives us a direct test of that question. If the ingredients match ours closely, maybe our system is common. If they look different, maybe the galaxy is more chemically diverse than we guessed. If these visitors keep surprising us, then perhaps the universe has many more ways to build worlds than the textbook picture in our heads. That should make you feel two things at once. Small, because our sun is only one star among hundreds of billions, and our planets may be only one style among countless others.